Okay, let's start off. This is the review. And the question has to do with water potential. And for some, oh, there's my drawing tools. Okay. And probably this has to do with the two cells together. Is that the question you have? Okay, so there's some assumptions that are made. And let's draw these two cells together, okay? And let's say then they are going to have a pressure potential, and let's say the pressure is going to be 0.1. I can't draw with this thing, and this one's going to be 0.2. And then let's say the osmotic potential is always going to be a minus 0.6. Goodness. And let's say this is a minus 0.9. Okay? So we have two cells that have a pressure potential that's positive, and that tells us right off the bat that these cells are full, that the cells are pressing against the cell membranes. The osmotic potential at 0.6 and minus 0.9, then we can add these together and get the water potentials of the cells, okay? Now, I've drawn the cells together, but when we start this, just theoretically, these two cells are separated. So this is going to be minus 0.5. Am I reading my writing right? And this is going to be a minus 0.7. That's the water potential, okay? Now think, this is, if you can visualize this, it's easier to work out the problems. Now, we take these two cells and we put them together. What is the only thing that's going to move between the cells? Water. Water is the only thing that's going to move between the cells. Which way is water going to move? But when we first stick them together, they've got this shared wall. Which way is the water going to move? Right to left or left to right? Which has a lower water potential? The only thing you have to worry about is water potential. Which one has a lower water potential? What's lower, minus 0.5 or minus 0.7? Okay. The confusion here is the highest it can be is 0, so minus 5 has more water than minus 0.7. Okay? And that is really confusing because it's negative. And it's also really confusing because a lot of times when we talk about it, we'll say 5 and 7. But we mean minus 5, minus 0.5 and minus 0.7. So then water's going to start moving this way. Okay? So water's going to initially move to the right, but then the water potential of the cell on the right is going to get less negative. So the water can only move to the right. And then also remember, you got water moving this way too, just not as much, until these two are equal. So at equilibrium, it's 7 and 5 divided by 2. You have to leave? Does that answer your question? Well, you can watch this.
Yeah.
Okay. So it's going to be 7 and 5 divided by 2. At equilibrium, so that's going to be what? So 7 and 5 divided by 2 is what?
Negative 1.5. Or negative 1.2, excuse me.
And then so it's going to be 0.6 for the water potential. Good Lord, I wish the drawing tools worked. Okay. Okay, now, so at equilibrium, the water potential of both cells is going to be minus 0.6. Got it? So I've told you that these are rigid cells and the volume does not change, which means then, let me go to another, that the osmotic potentials are going to be minus, oh, I circled the wrong one. The osmotic potentials are going to be still minus 0.6 and minus 0.9. So what changes? And this is what, and if you can think of it this way, it makes it easier. You've just forced water into the cell on the right. Since this is a rigid cell, the pressure is going to change. Okay? So the osmotic potentials will remain the same, and then the only thing that's going to change will be the pressure. Now it's going to be minus 6 equals, in this case, water potential is equal to minus 6, which is equal, in this case, is going to be minus 6, which means the pressure in this cell now will be 0. So it'll just be filled. On this side then, it's going to be then increased, okay? And it's going to actually increase to 3, right? So when we initially started talking about water movement, I sort of set up some rules like always find out where the lowest water potential is, where the lowest concentration of water is. That's what the full water potential tells you. And water's going to move from higher to lower water potential. And usually what changes in the cell is the pressure potential. So in this case, this one's going to be just right at a full cell with no pressure. Well, 0, it could be negative, so it's going to be that's just happened to pick those numbers. Now there was a mistake, at least one mistake on one of the exams, that when I uploaded the questions, I think I'll look at that later. I don't want to talk about it now, just to be sure. Okay? And it's actually easier to do if you think about what actually is happening, which is that water's going to move from a higher to a lower concentration. Since these cells are basically rigid, then the pressure is going to increase. In some of the questions in the exam, I think I had a question like, what if the volume of the cell is reduced by half? Okay, what component is immediately changed if you reduce? The first component that's changed is that the osmotic potential now is going to be doubled. Okay? The osmotic potential, the solute potential, I think I've used both terms. But the solute potential is dissolved solids. So if we half the volume, we're going to double the concentration of dissolved solids. And it's not perfectly linear, but basically, if you half the volume, then now you have twice the amount of solutes than you did, okay? And I don't think I'll ask you any questions like that because I had some caveats when I actually gave those questions. Does that make sense? No, actually, then to calculate for non-rigid cell, you would actually have to measure it. You can get an estimate, and actually in the real world, pressure is the thing that changes most rapidly. We talked about, in fact, we'll talk about osmotic potential again when we talk about drought, but some plants can actually make their osmotic potential much more negative by putting salts in the vacuole, so they can then take up brackish water, water that has a lot of salt in it. And not all plants can do that. So, and I think we talked about a bit about osmotic adjustment. Okay? Next question. Definition question. Yeah, you're going to have that on your take-home exam. Don't worry about it. I think I told you in class that's going to be one of the questions on your take-home exam. Guttation. Yeah, and all these exams have some things on it we've probably not covered, because I cover different things every year. I mean, there's 13 things that I have, 13 topics that I have to cover. Okay, I think this is the first one. Was mineral nutrition, or was nutrient uptake, I think, was the first one. Any questions about nutrient uptake? Any questions about nutrient uptake?
Oh, yeah, on the first quiz, the difference between, diffusion and bulk diffusion.
Okay.
There was something from the bulk.
Bulk, flow, or
Yeah.
and diffusion. Okay. Well, diffusion is, and I think those are both in water. I think I may have the wrong one. Ah, here we go. Diffusion and bulk flow. Okay. Diffusion is just movement based on concentration by thermal agitation. So if I I used to bring mercaptoethanol down, then I found out that I'm not allowed to do that. It's a very noxious, really strong sulfur odor. If I open a bottle of mercaptoethanol down here, you'll start smelling it after a period of time, because there's a higher concentration of mercaptoethanol in the bottle. And what's going to determine how fast you smell it? Let's assume there's no airway, there's no fans going off or on. So how can I get you to smell that mercaptoethanol quicker? What can I do to the mercaptoethanol? Can it heat it up? So it is movement from a higher to a lower concentration. Does not involve membranes. Things can diffuse across the membrane, but not much. And then bulk flow is the way water moves through a garden hose. So it's moving down a pressure, and it's moving, though, as a bulk. So diffusion, we're talking about individual molecules moving until they get to equilibrium. With bulk flow, water does not move through a garden hose one molecule at a time. It moves as that continuous column. It's being pushed by the water pressure through the hose. And that is part of the way water moves in the plant. Water moves in the plant not as individual molecules, but as a bulk of molecules, if that's correct English. The whole bunch of molecules at a time. And they're being pushed up and then pulled up. Diffusion is simply higher to lower concentration. You know, and let's see if, here we go.
What was the bulk diffusion of?
Well, bulk diffusion, did I ask that as a question?
Yeah, it was a question on the quiz.
Bulk diffusion?
Yeah, it said, like it gave like 5 or 6 answers. It was like, what causes molecules to come to something or other, like thermal, something.
That would-
It said diffusion, bulk diffusion.
I think bulk diffusion is probably not a correct answer for anything.
Okay, right.
I'll have to look. I
Okay.
mean, I'm going to do that video tonight about the questions. Here's diffusion. Diffusion in this model, there's an opening. So the movement of the white dots in here, and also remember the blue is moving over here too, but in this case, let's say we're dropping a drop of food coloring into water, then that's just going to move through here until the concentration of those whatever molecules are the same on both sides, and they're going to be at the same level. Okay, there's no membrane involved here. There's no ability for force to be generated. And let me go on down to the next one, where we have a membrane now. Now we're talking about water potential. We're no longer talking about strictly diffusion, though even through a membrane you're going to have things that diffuse back and forth. But now you're going to have these on one side. This is the lower concentration of water. So water is going to move through from the right to the left. And the water is going to keep moving because the water is always going to move from a higher to a lower concentration. And as it moves, the liquid actually rises. And the liquid's going to rise until the force of gravity, so the pressure then on this side is equal. So water is still moving through from the right to the left, but every time one moves in, then this force pushes one to the other side. Okay? So this could be water potential 0, and this could be 0 because you're going to have a negative osmotic pressure and a negative osmotic potential and a positive pressure. Okay.
And just the ones that are covered on this exam, like this water and nutrient uptake.
Water and nutrients on this exam. I think that was the 2 examples. Yes. Any more questions about water potential? Yeah, I think I had one of these on your quiz, didn't I? Or not? What did you have? You had a diagram on your quiz today, didn't you?
Yeah.
I don't remember. I keep adding and subtracting.
It was the AT. It had a.
Oh yeah, the ATP, the antiports and symports.
Yeah.
Okay. Yeah, I tend to use diagrams on the exams.
Yeah. I like them. I like being able to see stuff. I think it's much easier to be able to visualize it than to be, set out or whatever.
Next question. I only had 2 people come by today, and both of them asked the exact same questions about water potential, so. Sure. Mm-hmm. Oh, okay, okay, that's that last question, and you've got a capillary tube aboard the shuttle. And water moves, is it in this section that I talk about capillarity? Yeah, it's not capillarity. Is it? Come on, whole plant. I'll go over here and see. Yeah, here we go. And that's, no, that's it. So here's the closest one. Okay. So water moves in the xylem by a combination of, well, several things, but one of the things is capillarity, which is the movement of water in a very, very, very narrow tube, which is what the xylem is. And the movement is due to 2 components. Adhesion and cohesion. Now, cohesion is what keeps the water moving as a bulk, whatever that correct term would be. So water is attracted to water. Then adhesion is is the same. That's the way I can remember it, because I get them mixed, and I may have got them mixed up in class. I do all the time. Cohesion is water to water. It's the hydrogen bonding of water to water. And then adhesion is basically hydrogen bonding to something else. Okay, so the classic will be, and I guess they still do this, if you get your finger pricked and they'll put that little tiny tube and you'll see the blood run up in the tube. Okay, that blood is moving up because the water in your blood is attracted to other water molecules, and then it's also attracted to the side of the glass. So the smaller the diameter, the further up it will move. So the questions I think asked at the end was what would happen to that on the space shuttle, okay? So let's say we've got our capillary tube on the space shuttle. And let's say first I'm on the ground and I prick my finger and I put the tube absolutely vertically up and down. And the blood's going to flow up because of cohesion of water to water and then adhesion of the water to the sides of the glass. How far up is it going to move? What determines how far up it moves? When will it stop? If I have a tube that's 3 feet long, will it move up to the top of a 3-foot long tube? What's the force that keeps it from spurting out of the top of the tube? Gravity. Okay? So gravity is pulling it down. How much gravity do you have on the shuttle? A lot less, so it'll actually go up higher in the capillary tube on the shuttle. Just think about it. It's going up, and then gravity is pulling it down. So on the shuttle, and And they did this years ago on the shuttle. It's just going to keep moving up a lot. It's not going to spurt out of the top because it doesn't have anything, it doesn't have any force behind it. It will fill the tube. Okay, next question. We talked about root pressure, right? Remember that?
The roots are really powerful. That's why, when you see like, the concrete after, a tree's been growing there, it's all like pushed up, and you got one that's like way higher than the others. It's like, well, how did a root do that? Because, roots can produce like 100 pounds of pressure, like.
Mm-hmm. Yeah, you can see there's a popular thing they do with kids where you take is it plaster of Paris? Yeah. And you put seeds, dry seeds in plaster of Paris and just make a ball. And the seeds, the water potential of a seed can be minus 2,000. So even as the plaster is starting to dry, the water potential is so negative that water from the plaster of Paris mixture is going into the seeds, and they'll actually, as the plaster dries, it'll cause it to crack. And you can see where a seed has gotten into a crack in a sidewalk, and it will actually, the force is so great when the seed expands, it will actually crack the concrete. And we just touched on it. I used to teach seed physiology, and that's what I used to do my research in. And it was seeds. There's something we didn't talk about called the matrix potential, which is the part of water potential that's due to the dry makeup of the seed. Next question. No, I still have all those in there. Here you've got positive root pressure. And you can actually do this. You can attach a manometer and water the plant, and it's going to push the water up to a certain point so it'll actually move the mercury. There are better ways of doing that. And this, I told you when we went over this in class that you're going to have this on your take-home exam. Next question? That it?
Yeah.
No questions? Okay. Sure, go. Okay. And I will finish and post this online.